let's take the rest of the questions offline. And our next speaker is Xiong from Emory University. And she will be telling us about real-time aggregate monitoring with differential privacy.
Hello, good afternoon. I can't talk as fast as Rebecca, so I hope I cut down enough of my slides so I can make it through the time. First, let me say that it's a great opportunity. Thank you for the opportunity to be here. It's great to see both the theoretical results and the real-world example. What I'll do today is to also share with you one of our projects on real-time aggregate monitoring with differential privacy. This is a joint work with my student Li Yue Fan and professor, my collaborating PI, Vaidi Sundaram. So as Katrina mentioned, big data can have different dimensions. One of the dimensions is the velocity. Data is dynamic and they're changing constantly. One of the driving factors that I think is the social media or social sensing, right? People constantly have smartphones, GPS devices, and they can contribute a lot of the data. They can collect a lot of data from anywhere, anytime. This include the GPS information, GPS location, their symptoms they can report, their physical activities they can report, and the smart meters that are being installed at different households that can monitor the energy consumption and all that. So we've seen many of these applications like traffic monitoring, syndromic surveillance, and smart metering, and so on. So all these settings can be abstracted into this sort of figure where we have the individual data that are being collected constantly, continuously into a trusted server, and then they want to mine or analyze these aggregated time series data and share it with researchers for other purposes. So here we want to address the privacy of the personal data. This includes the location, speed data, household energy consumption, and all these. And of course, one particular requirement we want to address here is the real-time requirement. We want to do this online or as the data are generated. As a quick outline, I'll just talk about a simplified version of the problem, which is single aggregate monitoring, and then move on to multiple aggregate monitoring or spatial-temporal monitoring. And for each of these problems, I'll introduce our algorithms and give some quick empirical studies on real-world data sets. Not as big scale as Rebecca's AT&T data, but these are some real-world data sets that are publicly available. And at the end, I'll try to give a quick discussion and introduce some of our work in progress. So the simplified or the simplest version of our problem is a single aggregate time series monitoring problem. And here we have a univariate discrete time series X, which consists of a bunch of values X sub k at each different individual time points. Here K is a discrete time index varying from 0 to big T, and T is the length of our entire time series that we want to monitor, our monitoring period. And we can see many examples. This X sub k can be the daily flu count in the particular region or the hourly traffic count at a particular intersection on the map. So our problem is, given this aggregate time series, notice that it's already aggregated. It's an aggregated count. So given this aggregate time series X and the differential privacy budget alpha, we want to release alpha differential private series with high utility. So here, the privacy notion we use is the user-level privacy, meaning each individual user can contribute to each of the count at each individual time points. So it's different from the event-level privacy notion I'm sure we'll hear in other talks. And here our utility is measured by the relative error between the released time series and the original time series at each individual time points. Okay. And later, I'll just introduce quickly one of the applications we use or we apply on these release time series, outbreak detection. So there we use different utility metric. So given this problem and given the Laplace mechanism we have heard from Katrina's tutorial, one baseline approach is at each time point, given the aggregated time series value, we can just apply a Laplace perturbation on the original value. So given the X sub k, we can draw a Laplace noise and add it onto the original value and release the perturbed value. And because we have t time points and overall privacy budget alpha, so we have to divide alpha over these t time points based on the composition theorem, sequential composition theorem. So each of the perturbation gets the budget alpha over t. And as a result, our release time series would have a noise in order of t, big T, the total length of the time series. So that obviously is not a good idea. The amount of noise could be very large if our time series is long. So recently, there's a work that's been proposed. It's called Discrete Fourier transform approach. So it's a very smart idea where, given the time series, if it's too high, too much noise to perturb at each time point, then why don't we just transform the data into the Fourier, using the Fourier transform into the time domain, and then we just perturb the coefficients in the frequency domain. And once so the approach just applies the discrete Fourier transform on the aggregate time series, and then in the frequency domain, we just retain only d coefficients of that. So because of this, we can actually just perturb these d coefficients. And then after that, we do a reconstruction and get the original time series. So now you can see now we would have a perturbation error in the order of d, where d is much smaller than the big T. And we would also have a reconstruction error. So it shows in a paper that even given these trade-off between reconstruction error and perturbation error, the overall accuracy is still better than the baseline approach. So question?
So is it even necessary to do the perturbation? What can be shown after just doing the cropping of the chop digit coefficients in the frequency domain?
After we chop off the coefficients, we just do a reconstruction. Well, that itself doesn't have differential privacy guarantee.
So is there a negative result?
It's not a...
Oh, because it's not random.
Yeah, well, it's somewhat random, but we can't really prove that it's differential private. That's the... Yeah.
I'm sure we could cook up some bad examples. Not just
Some attacks, yeah. Yes?
If you're stacking the d largest coefficients, that depends on the data itself.
Exactly. So that's another argument we say here. Okay, it's hard to decide how many coefficients to keep, and that's very data dependent.
I just mean which ones they are also depends on the data.
Which ones are? Yes, exactly. So that's some of the limitations of this work. And in addition to these limitations, we also argue that this kind of approach can be only applied offline or in a batch processing mode, where you would have to have a period of the time series in order to do the transformation and reconstruction in order to be meaningful. So in our approach, what we propose is a approach we call FAST, filtering and adaptive sampling aggregate time series monitoring. There are basically two ideas. The first one is called filtering. It's really a post-processing technique that given the basic Laplace mechanism, we want to do some post-processing or some filtering to get a better educated guess of the original true value. So that's the first idea. And the second idea is the adaptive sampling, which is also very intuitive, very straightforward, since it's too much noise to be added to add to every single time point. So why don't we do sampling? We can just sample selected time points and do the perturbation. But of course, the problem is which time points to sample and how do we sample? So that's our adaptive sampling idea, where we use the feedback to actually help us decide the sampling rate. So this is the overall figure of the approach. We have aggregated data coming in, and it goes through a Laplace perturbation mechanism, the baseline. You can think of it as the baseline, the basic Laplace perturbation. And the perturbed value would go through a filtering component where we have a prediction and correction step. Prediction assumes there's an underlying model of the time series. So this is a model-based approach where we assume there's an underlying process model for the data. And use the prediction, we can get a prior estimate of the next time point. And then if we are at a sampling point, we would get a perturbed time value or a observed noisy data value. And using that, we would correct it and get a posterior estimate and release that. Okay? And then since we have the prior estimate and posterior estimate, then we would take the difference and treat that as an error or as a feedback and feed it back to the sampling adjustment component, help us to adjust our sampling rate. So the basic idea is if the prior and posterior, they differ a lot, that means the model is not very accurate in terms of helping us predicting the data value. So we need to sample more frequently. Otherwise, if the error is small, that means the model is fairly accurate, so we don't need to increase our sampling rate. Rather, we would actually decrease our sampling rate and save the budget for other more dynamic time points. So that's the overall picture. I'll just get into a little bit detail of each of the idea. So for the filtering, we would assume a process model that generates the underlying time series. So here is our underlying process, x sub k, and the next time point is x sub k plus 1. And to start with, we have a very simplified constant model or linear model where we say the value at time point x sub k plus 1 is only dependent on the value of the previous time point k, which plus a white noise. And the white noise is just a Gaussian noise with a variance q. So this is our process model. And given the x sub k, since it goes through the Laplace perturbation, and what we observe is z sub k, which is differentially private. So that's our measurement model. Given the x sub k, we're adding a Laplace noise and gets the z sub k. So now our real question in terms of the post-processing is, given this noisy measurement z sub k, how do we estimate the true state, the true value x sub k? So it becomes an estimation problem. And we can apply some basic Bayesian rules and all that. And it turns out the posterior distribution of the x sub k, which is our estimation problem, if it's a basic formula here, the only issue is that our likelihood function, given the x sub k, what's the probability of observing z sub k? This function is Laplace noise. So this becomes a little difficult. If it's Gaussian, it becomes very easy to compute analytically. However, it's Laplace noise, so it becomes difficult to compute. So we have proposed two options or explored two options. The first one is, okay, let's just approximate the noise as Gaussian noise. So notice here that the noise that are injected into the data is still Laplace. It's just in the modeling or post-processing, we're approximated using a Gaussian form, so that we can apply the common filter, the traditional common filter approach, to do the filtering and to do the posterior estimate. And another option is we use the Monte Carlo simulations to estimate the posterior density using the sampling importance resampling approach. So both of these two approaches, we experimented with them. And these are some details of the two approaches. I'm just going to skip them. So that's the filtering approach. And the second idea was the adaptive sampling, as I mentioned. This just illustrates the idea. If the data is fairly constant, we want to keep the sampling rate low. However, if the data is going through a lot of changes, we want to increase our sampling rate and get more observations. So how do we control this? The idea is using the feedback error, since we have the prior estimate based on our model, based on the process model. And if we do get a observed noisy value, we would have a posterior estimate using the either common filter or the particle filter. Then we can compute the difference or the error between the prior and posterior, and we can use that as our feedback error. And we use the basic PID controller, which computes the proportional, the current error, and the integral error, and the derivative error. And combining these three, we have these adjustment formula, which would determine a new sampling interval based on the error. And again, the basic idea is the error is if the error is large, then we increase the sampling interval. No, I'm sorry, increasing the sampling frequency and decrease the sampling interval. So those are the two basic ideas, and we did some evaluation on both synthetic data sets and real data sets. The synthetic data sets, we have linearly generated data and logistic data and sinusoidal data. The main motivation to try these different data sets is that since this is a model-based approach, our process model is assuming a linear model. So we might want to see if the data is indeed generated by a linear model, then the approach may work better than the data that are not generated by the linear model. We also tested it with several real-world data sets. These include the flu data sets from the CDC collected over a several-year period, including 209 data points, and the traffic data from the University of Washington Intelligence Transportation Systems research between 2003 and 2004, and another unemployment data sets. These two figures just shows or illustrates how the data look like. They do have different dynamics. This one illustrates the effect of the baseline Laplace mechanism and our approach. So the blue line shows the original time series data, and the dashed line shows the time series released by the baseline LPA mechanism. And you can see it adds a lot of noise because it adds noise at each individual time points based on the sensitivity. And our fast approach, because of the filtering, the post-processing, and adaptive sampling, it was able to reconstruct or gets much closer to the original time series, the released data. And you can see this flat lines is actually the effect or the result of the adaptive sampling.
What's the frequency of the data set?
The frequency of the data set?
Yeah.
What do you mean? Different data sets have different frequency.
the frequency of the timestamp that you're having for each data record?
Okay, so that's a good question. For this one, I believe it's the flu data set, or I believe it's the flu data set, then it will be hourly, not hourly, daily flu counts. So like every day. But now I have to double check on that. I can get back to you if I'm mistaken. We also did some more experiments using different data sets. So this one compares the result of Kalman filter and particle filter for different data sets. So the immediate thing we can see is that the logistic data and sinusoidal data have a much higher relative error than the linear data. This sort of confirms our hypothesis or our guess that if the data is not generated by the linear model or it doesn't fit with your assumed data model, then it doesn't work as well. So in this case, one of the conclusions we had is actually, well, any domain knowledge would be helpful. If you know your data, the underlying model of your data, then you can do much better things. Otherwise, if you're just kind of randomly testing your model, then it may not work as effectively. But fortunately, for these real-world data sets, it works surprisingly well. For these flu data, traffic data, and employment data, even though we don't exactly know the underlying model of these data, but by approximating this linear model, it works extremely well. And another quick takeaway is that the particle filter is slightly more robust than the Kalman filter because we don't need to tune the parameters. However, it does take more time. It's more time-consuming because of the simulation process. This compares the fixed sampling and adaptive sampling. The two lines that has a dip basically shows with different sampling intervals, we were able to achieve different results, and which is very intuitive because the trade-off between the perturbation error and sampling error. But with our adaptive sampling, it works independently from the sampling interval, and it's actually able to achieving almost optimal results that can be achieved by the fixed sampling. This shows the utility versus the different level of privacy for different data sets. Also in comparison with the baseline LPA approach and the discrete Fourier transform approach. So the basic message here is that the fast approach works fairly reasonably well. But one interesting factor is that when the alpha value, the differential privacy parameter, is sufficiently high, the LPA approach is actually good. So that's surprising, both surprising and not surprising. Yes, question?
For your transformation model, so how many levels do you retain in your experiments?
For which one?
For the Fourier transformation.
Oh, the DFT. We use the number that's recommended by the paper, but it varies for the data sets.
And what
Oh,
is the
one more
error?
question.
What is the error, the relative error?
The relative error is actually, for example, here is 1, and here is actually 10. So this is pretty frustrating, right? By looking at the absolute value of these errors, we feel like, okay, does it really work? The error is actually 100%, for example, when it's 1. Which is understandable because we have 200 time points. We have to divide the budget of 1 or 0.1 into these 100 time points. So this, I don't know whether we should characterize this as negative result or positive result, but the average relative error is fairly high. However, what I want to show next is that despite this error, which seemingly is high, if we are using this data for outbreak detection, in fact, for all these different data sets, our F1 metric, which is a combination of the precision and recall, is reasonably good. For example, for this flu data set, we're able to achieve 75%, or 0.7 for the F1 score. So I think that's a good message. Meaning, if we simply look at the error or the absolute error or the relative error, it may be really very high. But depending on what we want to do with the data, for example, if we want to do the outbreak detection, which is defined by a sudden increase in the data value in the time series, then we may actually get good utility from the data. Then we extended this work into multidimensional time series with spatial-temporal data, where we not only want to monitor the aggregates for one single cell, we may want to monitor the traffic counts for all the intersections on the map, for example. So we took two approaches, temporal modeling and spatial partitioning. And the temporal modeling is very simple. We just treat each single intersection as one single time series over time and just apply the previous approaches. But of course, we did some road network-based modeling for the variance. So we also did the multivariate time series modeling using the Markov models. And another interesting angle is we can also do the space partitioning, sort of considering the spatial dimension of the network, of the road network. Our first idea is, why don't we apply the feedback-driven sort of dynamic control on our space partitioning, spatial partitioning, right? If the data is going through a lot of changes, we may want to drill down into the area. If the data is sort of constant, then we can afford to go up. And we tried to apply this dynamic partitioning idea, and we failed miserably, and we're not able to get any good result using the dynamic partitioning. And our guess is that, or our sort of conclusion is that because of the noisy data, we're using the noisy data to do the control, to do the decision on the dynamic partitioning, and the guidance is just not as good as not doing the partition or dynamic partitioning. So we had to resort to sort of road network-based quad-tree partitioning or basic partition, static partitioning. And we were able to get some good results in this sense. So as a quick discussion or some quick work in progress, just consider my rump session submission since I won't be here tomorrow. We realized that the differentially private monitoring, sort of continuous publishing of dynamic data or time series data is a difficult problem, especially when the time series is long or if we want to do it forever. Or when the data is sparse. However, a lesson we learned is that any kind of domain knowledge, the model that might be used, that we might know to generate the underlying data, or the road network that we can use to help us partition the space, any of these domain knowledge could be useful for temporal and spatial modeling. And a related question that Rebecca also brought up is the dynamic budget allocation. So in a static case, you want to allocate a budget among different steps. But here, for the dynamic case, we also want to decide how to allocate the budget for different time points. Even if we have the sampling, for different sampling points, how do we dynamically allocate a budget? That's sort of online resource allocation, very difficult problem. And we're also working on a distance-based approach, which sort of similar or related to that, what Katrina has mentioned, instead of the model-based approach. And finally, we're also interested in looking at correlating data from multiple sources or multiple time series. Okay. With that, I'll thank you.
So let's take a few questions while the next speaker sets up.
I have one. In FAST, I didn't understand how you were doing the adapting in differentially private ways.
The adapting is actually already differentially private because we're not using the original data to do the adapting.
So I'm sorry, then what's telling you to change your rate?
Yeah, so we're using the first one is a prior estimate, which is used purely based on the process model.
Okay.
So using the observed value or posterior estimate from the last point, we can predict the next point value. So that's a prior estimate. And then if we have an observed value, which is noisy, which is differentially private, and then we do a posterior estimate.
Okay.
And then the difference between these two, we use this as a feedback error. Yeah. Thank you. Yes.
Because we consider mainly counting data and they are positive and discrete. So how about using some other more directly relevant models like Poisson model for the predictive distribution other than the Gaussian model used in common view?
Right, so that's a very good question. But here, our model is actually modeling the change from the last point to this point. When you were saying Poisson model, it's have to, well, yeah. So that's exactly, yeah. So it's not on the aggregate counts, I think. But on the other hand, related to that, we are actually applying some more complex models. So using adaptive common filter instead of the linear model. Yeah. Thank you.
Let's thank the speaker and